Thank you, Andre, for the fantastic introduction. Hello, everyone. And today I'm gonna talk about personal robots in the wild, like Andre said, and this is gonna start working. Sorry. There we go. So let's get into the basics. So what do I mean by personal robots in the wild? Is it what I mean by the wild? This is certainly the wild, the Hollywood stake of the wild. If for those who are not aware of this, the series, it's called Westworld. It's a HBO series about robots and androids. That are androids that actually are part of a Western theme park that you can go and be part of their stories. And so, as I said, Hollywood has exaggerated in the wild concept, but normally in robotics, what in the wild means is actually outside of laboratories, outside of your the researchers' comfortable environments where they can control everything. So in the wild, in the out there in the real world, it's often very difficult to control the dynamics of the environment and things. So it gets things not end up working the way they should in their labs. So, and are these personal robots? So, well, to an aspect, yes, because they have personalities. They have, they can adapt to a person. They can learn from a person. But they have what is called a reset in the story, so that they're actually reset after the story ends, so they forget everything. But if you were to put robots in the wild, we need them to for long-term interactions over time. We need them to learn from us and to remember their shared history with us, our preferences, our needs, so they can adapt to us accordingly. So what I mean by robots is actually this. So this is Rosie the robot from the Jetsons cartoon. It's a household robot that can do chores such as cleaning and cooking, and it can also take care of the children and to talk. It has a personality, emotions, etc. So this is the science fiction's way of looking at it. Also, I think I have this. Do you see that on your screen? Is that it says recording in progress notice for the shared screen? No? So I can close out. Oh, okay, that one. Perfect. Okay. Sorry about that. And for this robot, it's not that easy to make such a robot. It has many components. To be bringing us to our daily lives, first we need to make a robot that's actually with the robots, it's called the Maravic's paradox, where things like maths and computation are very easy for robots and computational systems, whereas mobility, like going around, or perception, like the understanding what is an object and where they are and so on, are not very easy things. They're much more complicated than it is for a child, for instance. So let's break this down to three simple components, what I call the body, mind, and soul approach of robotics. This is my take of robotics, by the way. It's no definition as such, but like the body is the hardware of the robot. It has sensors, actuators, manipulators, it's a structure, and then comes the mind, so which is the AI. You can take it as the planning, the perception, the control, the memory, the navigation of the robot, and finally the soul. So the human-robot interaction. So, for instance, if the robot needs to be social, it needs to communicate with people, and it also needs to have a personality and emotions if it's going to be in a human environment and interact with humans like humans. And that's exactly the path I took from body to soul. So I started my undergraduate from 2012 to 2007 to 2012. I did my undergraduate in mechanical engineering at Bosch University, specializing on mechatronics. And for my senior project, I built these robots, these small educational robots. We designed them, the chassis, and we built them from plexiglass And we collaborated with the Intelligent Systems Laboratory in the electrical engineering department to bring them to life with the sensors and so on. And these robots are used at the robotics control course, robotics control course of the university. 10 days still after the 11 years after since we made them. So they're still being used to teach students how to do navigation, how to do control and planning for robotics. And having mastered the body, after graduating a study class, I took on the next step in my journey towards building personal robots to master the mind and in computer engineering at Bose University. So I was part of the robot football, where these are the now robots that you see here. So they play 5-5, a robot, basically they play football, and a simplified version. With back in the time it was a red ball, now it's more advanced and so on. And I worked on the motion planning and the behavior planning, the motions such as goalie motions, kicks, and getting up from the floor, as well as the challenges that the technical challenges that the RoboCup had, such as detecting a whistle, detecting when the ball is, when there is no field lines, and so on. And for my master's thesis, I of course chose to solve a household chore as a task. So I chose dishwasher loading, which I do not like. But how everyone loads their dishwasher is actually completely different. So you can choose to optimize the spacing within, you can maximize the capacity, but you can also sort them according to their sizes. So that we decided for that reason to develop a user-centered approach in task planning and the manipulation of the robot. So we conducted several surveys to understand the preferences and priorities of people to apply them for a cost function, so that the robot can actually use this information when it's planning for placing dishes. So this combined object detection as well as planning, but this was a master's project by myself. So I actually brought it down to 2D tray instead of the 3D complicated dishwasher environment. Because when you think about it, you're actually putting them on the same surface. So you can simplify the problem as 2D and then build up on top of it. So 2 years ago, I went back to this work while at Eminox, and as I wanted to analyze whether the optimized models, task planning and manipulation, was actually what people wanted in the first place. So I showed them the simulation videos that you see there, and asked them, so what is it that what is the method that you prefer the most? And to my surprise, it actually ended up what they said they wanted and what they actually wanted was completely different. And this actually shows that it's really important to bring people in iterative design, in co-design together with them when you're developing systems for them, because you might end up developing an engineering approach that is optimized, but not something suitable for the people, and they might end up putting it in their houses without being actually using it or selling them back. And also to this iterative process, to actually go back to them and continuously ask them, is this okay? Is it what you want? Helps solve the problems over time as well. And another thing is to have these situated interactions, to actually show these videos, these prototypes before actually developing systems, just to say, oh, we actually made a survey, we made a market research, this is what they want. No, it might not be. One more thing that what came out was that each person had different preferences, which means that we can't just, devise cost functions that are based on what general population wants. Yes, they generally agreed on something, most of them, but there's also people that actually want something that is more than that, that's different and so on. So we need to actually personalize these robots. So now it's time to move on to the soul. So we got the body, mind, and now to the soul, and build actually these personal robots. But the first step towards personalization actually goes through recognizing a person. So while off-the-shelf face recognition algorithms achieve remarkable results these days, these are often trained they're often made for what is called a closed set recognition, which means that the algorithm has already in their system a lot of data, a lot of images of you, of everyone, so that you can actually detect them from then on. So the person who's going to recognize, it actually knows them beforehand. Whereas when you're putting a robot in the wild, in the person's house, it might be that your friends come over and you want them to be to introduce them to the robot, so that the robots can actually recognize them over time when they come again. So in that case, it's called first open set recognition. You need to detect that they're new, and open world recognition. You need to add them, learn them, and add them to your system. And such an algorithm is very difficult because of for deep learning architectures, because of the problem called catastrophic forgetting, which means that when you learn new classes, when you learn new data, you actually forget the previously learned information. So for that reason, you need incremental learning, and you either retrain all the information that you have from the previous users, and this is very costly. It depends how many users you have in the system, or find a system that can actually do this incremental learning. Another thing is that maybe you have a different hairstyle, different sunglasses or glasses that you're wearing during the day. So you want the robot to actually recognize you with those changes from day to day. And one more thing. So let's say the robot actually is supposed to recognize you in the evening, there's no light and so on. How is it going to recognize you just from face recognition? It's not going to work out because of the low lighting conditions. So in that case, you need multimodal solutions. You need to combine this face recognition with other modalities to provide reliable information. So such a system that can detect new users, learn them over time, do online learning to adapt to them over time as well, and do combine multimodal information did not exist before. So I created it and called it the multimodal incremental Bayesian network. So it's Bayesian networks, which are, I'm not going to go into details, but the probabilistic systems that can be adapted for this incremental learning. And I applied it to a long-term study. So it was a 30-day, about 4-week study that the robot you see here, it's called Pepper, actually recognized people over time. I think there was 900 recognitions in total for 14 uses when they came into their office and so on. Or when they would go out for lunch for the kitchen area, was staying in the kitchen area, and we saw that it actually significantly improved compared to the face recognition and the baseline open world recognition algorithm, from raising it from 90% face recognition to 94%, which is good, but still it's a small population. In order to be able to generalize these algorithms to results of these algorithms, you need actually big data. So that's why I created this multimodal long-term user recognition data set using the IMDb Wiki celebrity data set, which has images of celebrities from movies, from TV series, as well as red carpet events. And it has very challenging conditions, as you can see, either people with different like completely different hairstyles or different makeup and so on, so that it's really difficult to recognize. So the color over there, or very different facial expressions or dark lighting circumstances. So I used 200 of these celebrity people and about 13 images per person to create this simulated human-robot interaction data set, where they're as if they're talking and as if they're meeting a robot in certain times of the day. So for the multimodal recognition, I also combined face recognition with gender, age, height, and time of the interaction. So these are actually modalities that the first parts are modalities that you can actually extract from an image as well. So these are called soft biometrics that do not recognize a person by themselves, but helps improve the recognition as well. So for this face recognition on the robot, the Nike face recognition, it actually only recognized 30% of the data. Whereas with my model, it was 60%. So it was significantly improved, and also significantly improved compared to the baseline model, which was a extreme value machine. It's an open world recognition method. And it also showed, another thing that it showed was that using online learning people's differences, it actually decreased the bias caused by the face recognition. So face recognition, it actually introduces these bias. It recognizes some people better than the others. This is generally due to the way they're trained. It might be that there is racial differences that it causes those biases, or that there are not enough data on certain aspects of the person. So what online learning did was actually to make people's recognition equal so that they can all be recognized equally. I have, by the way, if you want to use this data set or the model that I mentioned, they're all available on my GitHub under the links you see there that you can ask me later as well. So now that we can recognize people, let's get into personalizing the interaction. One important area where personalization can make an impact is socially assisted robotics. For instance, a robot may improve the motivation and adherence of persons to a cardiac rehabilitation, which is a therapy that is prescribed to people that have heart problems, like a heart attack. It's an 18-week therapy that is intended for 2 sessions per week, where you go to the hospital for about an hour session every time, and it's a group session. It's about 20 people that a few medics, the medical staff is actually taking care of, and then so that they can go on the treadmill for intensity exercise, as well as doing other dancing and warm-up exercises. But the problem so we collaborated with the Fundación Cardioinfantil and Colombian School of Engineering for this work. And what they told us that the adherence and the motivation of people to go to this therapy for 18 weeks is actually very low. So that people, when they start feeling better, they're like, oh, I'm feeling better, I should better just stop this because it's a lot of work. They said we want them to keep on coming because it's really vital for them to complete the whole therapy. So that's why we developed this robot for assisting in the therapy. It's a now robot, again, as you see. And we also use a tablet here that you cannot see, that it and a few sensors on the treadmill to monitor the patient during their treadmill therapy, to send this information to the robot, which can give feedback and motivation to the person throughout this 30-minute exercise. And we also, in case we also had from the medical staff information about their warning levels for their heart rates per patient. So it depends from patient to patient, and so that they can enter them, and the robots can alert the medical staff saying, "Hello, can you come over here?" In case the person's heart rate reaches above a critical level. And then we personalize I personalize this interaction by recognizing the user by the algorithm that I mentioned, but also to using their name, tracking their progress over time, as well as their adherence if they're attending their sessions as they're used to, as they should, twice per week. We deployed the robot at the Fundación Cardioinfantil Hospital in Bogota and Colombia for 2.5 years. So this was completely autonomous. And so this is in the wild. Things can go wrong here. It's a lot of sound. I'll just go back and rerun this if I can. Yeah, there we go. There's a lot of elements that you can see around that can just go wrong. You can even see that the robot might have fallen a few times from this from the table over there. And the researcher you see here only interferes if there is a problem with the robot. So it's the person can, the patients and the medical staff interact on their own with the robot without the help of the researcher. And there's loud music going on, as I said, so we didn't use speech recognition. We only gave feedback, and we only took from the patient the health measures like the speed and the gait, but also the heart rate. And we didn't take any verbal input because speech recognition might not work in such a scenario. So we had that they report their exertion level through the tablet interface. So we compared the tablet where no feedback is given, but the medical staff, of course, comes and tells the patient how they're doing, gives them motivation, like in a typical cardiac rehabilitation scenario, compared to a robot, which gives immediate feedback and motivation, and the personalized robot with the specialties that I said. And we had normally 43 patients to start with, but unfortunately, COVID happened. So towards the end, so we had to stop, some patients had to stop the therapy. So we had 26 patients in total finishing. There were also others that dropped the therapy, like we initially suspected, because of this motivation aspect. But the results were actually fascinating. So robots, compared to the traditional tablet condition, they actually improved the health of the person, the cardiovascular functioning, significantly. So just using a robot, whether it's personal or not, actually improves the health of a person. Also, they improved their motivation and endurance. So the patients were attended to the robot conditions, and then also forgot to mention, there was only one patient per session was working with this study, so that we don't have interfering conditions. But there were people that were really interested when the person was actually in the session with the robot. There was other patients that were asking, so how does this work? I want to be actually part of this study too, and so on. And it also enabled prompt detection for critical conditions by the clinicians. For instance, a very, very important case was when a patient started having a heart rate that went above the critical rate. So he's actually started having a heart attack on the treadmill. And the robot immediately let the doctors know, because it could detect that the heart rate was higher. So that the doctors immediately came, decreased the intensity of the therapy, and referred them immediately to surgery. Basically, the robot helped detect the heart rate, helped detect the heart attack, and helped save the person's life, which is an amazing case. And we didn't want that to happen, but we were really happy to see that we actually helped not only that patient, but also all the patients' lives get better, that their health get better in that case. And the results were all great. We were all happy, made a lot of papers. The clinicians were happy, the patients were happy. They actually recommended the robot for everyone to use. But there's also that we saw that the personalization actually elicits and maintains the engagement, the person's social interaction and the gaze with the robot over time as well. And there was an interesting case. I'm going to run this again, just to let you see. So the robot gives a feedback, and the person says, "Yes, sir." The patient, she knows that the robot's not understanding anything the person is saying, but they actually were replying back to the robot. They were saying nice things. They were looking at the robot, and they were so they were actually trying to make an interaction, which, as I say, it's gonna be really difficult in such a scenario. But brings me back to the social aspect of the robots. to communication and to dialogue. But we can do that in a more quiet setting. For instance, a cafeteria, a cafe. So let's say you walk into your favorite cafe and you'll go like, I'll have my usual. I will tell you, there's a very little chance that that barista is actually remember what your usual is, because he or she sees actually hundreds of people every day and they keep changing, their preferences keep changing and so on. But for a robot, this is actually an easy job. You can just save it in a database and say, okay, so you like small coffee and cookie. This time it got this one, and another time it also got this one. So this might be their preference, and so on. So you can actually tally over time what's the person's preference to personalize the interaction. That's why we built a personal barista robot using, again, the Pepper robot. Just going to step out so you can see this interaction. So here the robot, for instance, is asking, oh, hi, Pauline, welcome back. Would you like to have a medium latte and a chocolate cookie again, I think? And the person says, no, I don't want that, thank you. So then the person can now change their order and then want something else, so we can update their preferences over time. So we used a rule-based dialogue manager, which is basically using templates. So when you're ordering something, I would like X, replace that X with whatever you want in the order. So they can save those X's into this database and learn from your preferences in a very rule-based structure. We created both a generic robot that actually asks all the time what you want. It's a very, very typical cafe scenario, versus a person robot that remembers what you want, that recognizes you using, again, the algorithm that I mentioned. And we deployed this robot, again, in the wild, in an international student campus in Paris, which means non-native English speakers, but the interaction was in English. And with 18 participants as well. Again, this is all in the autonomous, and there's a researcher that you don't see back there. And this is from the real interaction. This is not a demo. And the ones you saw before, again, from the real interaction. None of this is a demo. And the researcher only only interferes when there is a systematical problem that the robots break down or something. Otherwise, it can go on. Well, what can go wrong, right? Well, we faced several challenges that negatively affected the user experience. For instance, due to unreliable speech recognition or pronunciation, or weak internet connection, short sentences, quietly speaking users, and so on. So that there's a lot of things that you would think in a normal cafe you can actually overcome, but it was still very difficult. And the second reason of failure was that people said some things that are not in the templates. So I was the one writing all these templates based on my all the times that I went to cafes and so on. And of course, even though I've written the hundreds of sentences, there's still things that people can say that are not in those templates. And in that case, a rule-based architecture does not support that. It will just keep on saying the same thing unless you say it in the way that it's supposed to, that it's expecting you to. For instance, in one of the cases, the robot asked a yes or no question, and the person instead said, I want lemonade. And they continued asking for that lemonade for 7 minutes. There was a very patient person. I would have given up, but they kept on going. So, and these things, these negative parts were actually building up for personal robots, for the personalized robot, because they were supposed to remember all these preferences, was supposed to recognize the person, and so on. All these additional aspects made actually the interaction worse for the people. But they actually enjoyed, those in the personalized robot condition actually enjoyed the interaction more. They look forward to the next one. They prefer to interact with that robot over a real barista, for instance, which suggests that personalization can actually mitigate the negative user experiences. However, customers, as I said, may not be so patient in a real-world scenario, so we needed a more robust solution that can enable fully autonomous interaction in the wild without losing customers. So we used data-driven architecture, so from rule-based to the other end of the spectrum, where it's, as most people say, it's a black box, so you feed the data and you get a response. What these models were that I was using were mostly memory networks, which was an attention-based model, pre-transforms, I might say, it's a similar structure, and a sequence-to-sequence model, that's a generative model that can encode and decode data to generate responses, whereas memory networks was a retrieval-based model. It will just retrieve something from the templates, similar to rule-based architecture, but more autonomously, that it will detect these patterns in the system and will find a response accordingly. As I said, for those rules that I created these burst of data sets, again, available online and GitHub, that I used to train and evaluate these models. And I saw that the generic dialogue, so if it was, what would you like for an order, which size, what extra snack would you like to have, and so on. If this was the interaction, then these data-driven architectures, especially sequence to sequence, achieves near perfect responses. It can almost get 99.85% of the responses it got correctly. But when you use personalized long-term interactions, when you're supposed to remember to, given the recognition information, recall that information, completely data-driven, recall that information from the data, the previous data, that who given either a name or just the ID, who the person is, their order, and so on. We actually saw that they're quite not there yet. So they're only the best one which was memory networks, only can guess correctly the 71.81% of the responses. So what does this mean? And what was the reason behind this? Well, the reason was because they were not able to learn new interaction. They were not able to learn new information. So what is called lifelong learning, so they can incrementally expand over time. These were not these models, the continual learning or lifelong learning. They were not able to incrementally learn new information or use that information even if they can learn it. We can't, which basically means that you can't just plug and play those data-driven architectures into personalized long-term interactions. So since data-driven models were not the answer, I turned to what is in between. So rule-based, data-driven, in between is probabilistic models. For instance, a partially observable Markov decision process. What is it? Basically, think of it as like this. You can be in a certain state, but you're not really sure if you're exactly in that state. If you're exactly in the, or for instance, like in the order or that you're supposed to ask for your size, then you prescribe some probability to it, and then you can go back and revert an action if you're when you take that action and you see that you're actually not in that state. For instance, again, what it does is that it estimates the future rewards, the future consequences of its action. So if I do choice A, I actually keep on going, then my battery will die. I will actually lose 10 points. Whereas if I go to charge my battery, I'm gonna live. So that's a reward. So this is a typical partially observable Markov decision process. And you do that action, you decide on that action based on what you think will happen, and you apply that to the real world. And then based on what actually happens, you update your beliefs, and there goes the next cycle. Where can this be suitable? Well, imagine a character that has a personality, emotions, and mood, and that can actually adapt his behaviors based on your emotions and its own emotional states for multiple people as well. So this is what we created at Disney Research, so that we can estimate the user's models. We can understand whether, for instance, if you were to feel angry and I say something happy to you, would you go from happy to angry, or would you go to neutral, or stay stay in that angry state. So it can change from person to person. So it's important to have a separate user model and to actually learn per person over time, what are these responses, what are these consequences of your actions. We use how much a person is smiling to understand their emotions, as well as the sentiment of what they said. What is if you said something negative or positive when you're replying to this agent, and as well as the speech prosody of your voice, if you sound negative or positive from that. And we combine this with the prompt TP to understand which state the person is in. For applying this to this agent, you see over that very, very cute agent. It was a virtual character. We had people interact with it in pairs, and the agent would give a scenario where it did some action. It ate its friend's watch, and it's asking you for your advice. So it's like, should I take responsibility and tell my friend that I ate this watch, or should I just give the fault to them because they left the watch with me? So we had the personality. We used the ocean personality. So we had openness, conscientiousness, extroversion, agreeableness, and neuroticism for the personality. And imagine an agreeable agent where all it wants to do is to give positive feelings in you. It's really like, oh, whatever you say, oh, you don't want to talk with me, that's okay. And another non-agreeable agent where it's trying to annoy you, but then for the fun of it, of course. For instance, oh, you're here again. Okay, fine. You know that this is a bad day for me, but I'll tell you anyway what happened. And so on. So people interacted with these two agents back to back, and we told them that they don't know what you tell each other. So they are completely different agents. And we wanted to understand if the emotion model that we used, which is based on the literature from Casapetal's work, that can actually show in terms of mood and in terms of emotions what we think the agent is trying to portray, as well as understand whether the personality is suitable to the one we are actually showing. And we actually had validated all of those. People actually thought that, but there were really interesting responses that came up as well, because people, for instance, interacted with the non-agreeable agent. Then when they were interacting with the agreeable agent, they were actually more mean to it, for instance. But this is all, we couldn't detect this, but this is all researcher observations, for instance. And now let's go back to the wild. For the past few slides, I've been showing social robots and agents, but how about industrial settings where robots collaborate with workers to make products that are without any verbal interaction? For instance, creating furniture for the hospitality industry, or buffets and such. This was at Evinox, where I was working for 2 years. They, as I said, they produce service equipments like buffets, restaurant and meeting room furniture, and service cards for the hospitality business from around the world, such as Marriott's, Hilton's, Accor, Sheraton's, and more. In such a setting, it's very important to provide customized solutions to customers, so that it's necessary to adapt what they want, because all these furnitures, they're not they're made, but they're also changed according to what the customers really want for their own hotels and such. So it's important to make a customized solution that can the robots can do as well. In this case, the robot's completely autonomous and it's a collaborative setting. The worker does part of the work and the robot does the rest. So you want to make sure that the work is not repeated and the robot can actually adapt autonomously to this interaction from different products without much change by the worker. In another setting, this is actually controlled by the operator for the welding. And in that case, you want semi-autonomy. You want the robot to detect where to start the welding, so the the operator does not need to actually precisely set everything up. We can do that precision afterwards, but you want a robot to actually take the lead first, and then you can build on later, so you can decrease the time for production. And another way to improve the production is to provide customized solutions to the customers prior to the production. For instance, through virtual reality, you can show what the buffet could look like to the customer, so that you can solve and adapt the model before you actually start the production. And the person can, with the headset, the virtual reality, it can interact with all the environment. It can like move around things to know if, for instance, if the waitresses or the chefs, how they can interact with the system beforehand to get things faster and reducing the cost of production. And one other use case for customization is a smart buffet. The screens you see there actually describe what type of food there is, and also their ingredients, their allergens, and calorie information, and the amount of food there as well. So if the food was the dish was about to run out, you could the waiters would automatically know this from their system, have an alert in their system, so they can go and replace it immediately without having to check multiple times. And it doesn't have to be like big hotels with multiple stuff for this. It can also be the restaurant of this lady, where she can enter her own dishes, so that she doesn't need to know any technical information. They can just all enter her own dishes, and it could decrease the time she needs to create for this while having a very technological solution. But after a few years, when she retires, and she might start feeling lonely because she's used to the hassle and the amount of people around in the restaurant. And now that she's starting to live alone in the house, she might need some social and emotional support. And that's what we here at KTH are working on. We're trying to develop a companion robot for older adults that can interact with them in their daily life, which means that the robot would need to talk to them and learn from them, so that it can personalize the interactions based on their needs, preferences, and so on. But of course, to create such a robot, we actually need to know what people actually want, what these older adults want, what do they expect, how can we incorporate a robot such as a companion robot into their daily lives. That's why we decided to do co-design, participatory design approach, to learn from them, to interview them, to have them interact with the robots, so that we can understand what are the challenges in these interactions, and develop a robot accordingly. And but for this system to be able to converse with a person in a day life, you need this dialogue architecture, right? So I talked about rule-based system, data-driven architectures. This was all pre-ChatGPT. This was all the current large language models, the foundational models. So now those things, like, they all needed either user input, and they were not flexible, or they were flexible but were not suitable for personalization. What about these large language models? Can we make them actually personalized for long-term interactions? Because again, these models, they're made for this single interaction, for that one talking with the person and giving them advice on something, whatever they want, but for this one time. Like, can they actually hold this interaction? Can they actually remember and learn over time? Again, it's called lifelong learning. We wanted to see that. But we didn't use ChatGPT, and the reason you see here is because it has this, it's actually an instructional model, and the name is very misleading, because it doesn't do chat. It helps with instructions. It helps give you instructions, but it's not a chatbot, because if you were to ask, what do you like? How are you? It says, as an artificial intelligence, I do not have personal preferences. I do not have feelings. And we didn't want that. We wanted a companion robot that you can actually talk like a person every day. So it's needed to have these personal preferences and so on. And for those who are not familiar with large language models, they're deep learning algorithms that are trained on large data, a lot of data, and they actually have billions of parameters. They're quite big. And what they do is they predict the next textual input given the previous information. So we're similar to the data-driven architectures. They just generate pattern. They just learn their patterns and generate information based on those patterns. So we didn't use ChatGPT. We used GPT-3, the model right before that, which is not an instructional model. It can actually have these personalities when you tell it to, when you give this prompts to it. So I think that this has this personality. So as I said, we use this participatory design approach to understand the needs of the elderly. So we conducted interviews with 6 elder adults, to semi-structured interviews, and they also interact with the robot, which had a personalized companion prompt. So that.
Hello, I'm Irfan, the personalized companion robot. What is your name?
My name is Elizabeth.
Nice to meet you, Elizabeth. What do you like to do?
Oh, I like to have a nice chat with you.
That's great. I love to chat too. Do you have any hobbies?
I read a lot, and I also like to pick berries.
So they interacted twice with the robot, once where the robot gets to first know them, and the second time where the robot actually learned from them and could actually remember this information. Just gonna skip that for now.
Hi, Elizabeth. Nice to see you again. What have you been up to since the last time?
Like this one.
I have come here with the bus to meet you.
Well, we actually had a lot of challenges while doing this interaction. So that the people.
And what have you done? What have you done?
That actually the robot, as you actually could see over there, frequently interrupts the person.
Yes, I like broccoli too. I use broccoli very often for a soup. And I like.
Yes.
And I like to.
Broccoli is a great vegetable to use in cooking.
Yes,
Thanks for sharing that with me.
I like to cook it in steam.
So
it's better to cook it in steam.
That the robot
Do you
yes.
use?
Steaming is a great way to cook broccoli.
Oh.
Thanks for sharing that with me.
So you can see that the robot actually had no other. So it's very difficult to see, but the robot's just looking at you. So we didn't have other measures to let the person know whether it's their turn taking, and the robot doesn't listen when it's speaking, or when it's thinking, when it's generating response from the GPT-3. So when there are several times that the robot actually interrupted the person, but also people, because they said something, they assumed the robot actually understood what they said, even when the robot was talking. So there were a lot of problems due to that as well. So what we did was actually to, later I'm going to talk about it, but to actually have a red light underneath and to gaze away when actually the robot's thinking, when the response from GPT-3 is being generated. So you can give more information through signaling that the robot's not listening to you, the robot will not hear you. And another case that happened was that the robot would give a very repetitive response.
I like to be out in nature.
That sounds really nice. I love nature too.
Wood with a lot of what is called moss.
That sounds really nice. I love nature too.
Want to know what I see in nature? And I'm also.
That sounds great. I love nature too.
So even though this model was completely autonomous, we had no interaction with it. Well, there's our end that it didn't actually use a rule-based system. It generated these responses that are exactly same or very similar to what it previously said, because these responses actually trigger a response back. So it's thinking that it actually says something good, so it keeps on saying it. And so there's exploration and exploitation circumstances in such algorithms, but the exploration and the exploitation was actually in the middle range. So it wasn't actually so low that because we were doing personalization, but still these kind of things happen. And one other case was the superficialness.
I love the cinema too. What's your favorite movie?
I don't think I have one favorite movie.
What is your favorite book?
I have no favorite book. There is not. I have read thousands of books. I have not one favorite.
Is there anything else you would like to talk about?
Yeah, do you read the daily papers? I like to talk about books, but I don't think you have read the same kind of books as I have done.
So as you can see, it's very superficial. The robot keeps asking, so what do you like? What do you do like this? Do you like, what is your favorite? And it doesn't, it's not very suitable for these older adults, which has, as she said, she read hundreds of books. She won't remember one favorite one. And when she actually tried to talk about it, this was English model that we were using, so you wouldn't understand the Swedish author. So there was a big problem there as well, again, with the speech recognition. So we decided to change the prompt to make it feel more empathetic, to make it feel more like social, emotional support agent rather than a chatbot. And it actually worked better later. And one last problem was...
What do you like to do for fun?
Alltså det står ju helt stilla. I like to see a movie.
Christina, you like to go to the circus. Do you have a favorite act?
So as you say, because the robot was talking in English, and this was and in Sweden it's really very a lot of people are bilingual, they can easily speak English, but for older adults it's less the case, and it's been such a long time they do not speak in English. It's not so easy for them to actually speak with the robot in English. So that's why, given all these problems, we decided to change the robot a bit and update and use a Swedish model, just the GPT-3 in Swedish, which we didn't know back then was possible, but then yes, it is possible, so that the robot can actually talk to them in Swedish now, and again, more personalized way. So this is the last part. We decided to make these participatory design workshops with 28 older adults over for workshops here actually at the Digital Futures. And we asked them, so given these everyday scenarios, what do you like? What do you think of this? Do you think this robot is suitable? What type of conversation would you like to have with the robot in these scenarios? As well as have them again talk to the robot with these updates and interview them afterwards about their experiences, as well as provide a lot of questionnaires. So, well, I'm still analyzing the results. It's a very recent study in the last month. Did we fix those previous problems that I mentioned? To an extent, yes, but not fully. We also, because that red light, for instance, actually helped people recognize that the robot was speaking, but they were not always following the red light. It's very difficult to follow. So they still had these interruptions, for instance. And but still, there's a lot of interesting cases coming out, especially one that is actually quite typical now, and a lot of this letter has come about because of that. It's the fact that it hallucinates, that it makes up facts, and is very certain about that as well. For instance, in this case, the
Moa Martinsons bok Mor gifter sig är en svensk tv-serie som gjordes 2011.
It says when the person after
Jag trodde den gjordes 1979.
Sure. Yeah, I'm sure it's 2011.
Nej, Moa Martinsons bok Mor gifter sig gjordes 2011.
Jaha, men då kanske det finns två
tv-serier.
tv-serier.
There's not. But they actually changed a person's mind that actually she knew the answer, but she changed her mind because the agent was so certain of itself. You might think of them as for instance, know-it-alls that doesn't know exactly all topics, but pretends to know and pretends to be very certain about it as well. It's a really big topic, very big, challenging situation. For instance, if they ask for the weather, gave a wrong answer. They ask for a cinema, gave a wrong answer. And this can have actually even more very challenging situations, for instance, for medicine, if the person were to ask about medicine and it will give a wrong recommendation. So are we there yet? Are we gonna have the Rosie the robot in our houses soon? Unfortunately, not yet. We're still working on that. You've seen all these challenges. You've seen all these robots out in the wild talking with people from all different aspects. And I'm not the only one from working on this. For instance, there's the workshops that I'm coordinating that I founded 3 years ago with amazing co-organizers that have people presenting, as well as having in panels, the experts from industry and academia, that you can actually watch online if you go to the website. They're all available on there. And there's also the early stage researchers work that are currently working on developing these personal robots out there. And this workshop actually has 70 to 100 attendees each year, showing that it's really important topics to keep on learning, to keep on actually investigating further. And personally, I wouldn't be able to do all of this by myself. This is all thanks to a collaboration of fantastic people, my wonderful supervisor or Mark with gears on top, as well as my co-organizers for the workshop. And I definitely suggest you to check all their work from the papers and so on that you can find actually on my website. If you go there, you can also find the links on my GitHub, and it's all in there. And I would also, if you have any questions now, I'm happy to answer them, but also through LinkedIn and email later. So thank you for listening.